Hi to you, my friends. Today, I'm gonna show you an amazing item that I scavenged somewhere, and it's like a treasure for me. Although it was somehow scavenged before, and I found it like this, and an electromotor and a gearbox set attached together, and around there I found some cylinders, like though I think it's a printer or something item, and part of that printer here it is. I actually scavenged it from 6 feet. I actually scavenged it from 6 meters tall, and I pushed it, then it fell into somewhere I could catch it, and it cracked. This crack does nothing to do with its applications, and first time I thought I'm lucky. I must get a lottery ticket because I thought it fell on this and bent it. It's an useless item. Maybe we can use it later. I need it to make a mixer. So time-consuming and labor-intensive work that I do for mixing chemical compounds and even culinary compounds that I make for cakes and baking and such. So let's get started. Here is a brushless DC motor without that flux ring you always see around these conduction motors, and here it is a tiny bit part. It is an Hall effect sensor, and you can see there is a magnet around here somewhere. I think this dot means it's gonna attach somewhere here, and a bipolar magnet will rotate and says with these 3 wires into controller how many revolution per minute it have, and how can control that printing or some sort of things, the stuff gonna happen into the heart of the machine. First things first, we need power, and an electromotor like this have 2 contacts, which contacts 3 induction coils around this motor, and will rotate this rotator in the middle of this motor. So what's better than an item that called power is itself? It's a computer, PC computer power, and you already saw that in desktop PC computers, and some information on it, some random stational voltage you can see in the information technology devices and all over the world and in all machines, these voltages are so common. So we can attach it to power network outlet. Come here, outlet. Oh, I crashed something. It's my outlet and my mobile phone charger attached to it, and we're gonna get some sketchy boys. These two. I don't have any reciprocator here, and oh, sparks. Shit. It means it don't have a good contact in that little holes. Good contact is so important. So I contacted it and it's powered now into this little K. And when you get on this K, you can see this little fan starts to push air out. So I attached some control cable in it before. And when you wanna power this thing you must attach this green wire into this gray, or I don't know, this purple wire. Then I attached it, and you can see it's not running. So carefully, without contacting anything else, I'm gonna push it into this gray terminal. Yes, what's going on, boys? And some electrocution in here. I don't know, maybe it's around 12 volts, and it knows it's gonna run. This is it. We hacked it into our power supply now. It's not a computer power supply anymore. So I picked one of black wires, and always black means negative, and we love blacks, and we not love negative peoples. Diggity diggity boom. I bought a battery, 9-volt battery for my multimeter. I will put it in 20-volt direct current. This line under voltage means direct. Make sure high voltage is not on, and some negative means some error like fuses and such, because last time I used it I blowed not a fuse. It's ridiculous. I blowed my good probe. This red probe was attached to it and it blowed up. It's not contacting anymore. You can test it like that, like though. Put it on buzzing and attach it. Nothing. But other black one, always blacks. We attach it to common, and you can see common in this diagram comes below. What happening? Focus, you fuck. it always listens. This is being common, and we are in buzzing sign, and we can hear some buzzing in here. So we need those anymore. We don't need those anymore. I bought some new probes, and these probes are not as good as those ones. Also, you can see from mold lines and everything, and restraints on cables. Those are pro. But something is occurred to my mind. The wires, it have slightly softer wires. It can help, and we need to probe something low voltage, and voltage, amperage, and resistant in low current lower than 10 amps indicates here. So we attach red to it, so harder than before, more chintzier, more harder, and we can attach it here. So we test them. Always test everything. You cannot believe everything can go wrong in here. So that we have multimeter ready, we put in maximum 20 volts and check airflow. It runs, and negative to negative, and diggity diggity boom. Those are orange cables, and as you can see, orange gives us 3.3 something 78 volts, and it's enough for testing this. Always go low voltage, then increase your steps. Even you haven't volume mounted, always go low voltage. Even if you have that sort of volumeable power supply, start from low voltage and low amperage. It have constant stational amperage and voltage for information technology uses. So it's so reliable. It detects everything and don't have any peaks in it. So I think I have, oh, you see that spark? We don't have airflow anymore because this wasn't positive direct current. And these red ones, I don't know, I must check them. Maybe they are 12 volts or so. It contacted to body of this, and always body contacts with ground or negative, and it fails this fault, and this fault makes it off. So we restart it once more. Do I feel any airflow? Okay guys, we hope I duped it. Maybe something blows in it. I think it blowed up. I disattach it and then reattach it from main power source and start it again. Wow. Voila, it works. So make it farther away from those thingies. Attach red first. Red means positive and negative. 5 point something. 5.5 is always acquired for information technology use. So we are here and test blue. What voltage have blue? Oh, 11 and something. It's 12 volt. Actually, there are some faults in it. That's a scavenged power supply. So we looking for something more than. Oh shit! I didn't hit the record button. So always start low voltage. Some hoopa-joop happened here, and unfortunately you can't see that anymore. It passed. These live positive wires contact to body of this power source and it fault, and I started going on and off with it to feel the airflow that it works or not. I disattached from main supply and it worked. So we can continue. It's better because it's gonna make video shorter. And we tested it and we catched in a stripped wire of orange ones. We tested blue ones. Blue ones was around 12 volts. It's less than 12 volts, so we know that is a scavenged power supply, and it may have some problems, you guys. So we don't need multimeter anymore, and we can use these props as in jumper cable. Yes, jumper cable. Cable that jumps and have tooths like in an alligator. So safe. Where are you, Red? Red always escapes. I love the red. Red is so naughty. We attach red to orange. Oh my gosh. We strip some of these condoms over these wires, and it's not more important that which gonna contact to whom. Okay, really slow it turns, so you can see it turns. How many revolutions per minute it turns, and how many revolutions per minute after the reduction in this reduction simple gears will we have afterwards? I show you in a short time. I dismounted power supply from power network and we don't need any electrical for a while anymore. Papers. First, you count how many tooths is around the main gear that escapes from main shaft of the electromotor, and it's easy. And just pick some sharp thingies and count. I'm so lazy, so I count quarter of that, like when we count the vein pulses, and I quadruple that. That was 5. So total in first shaft is 20. We need some older pen so this Sharpie can work. We have in one gear 20 steps, and second one we start from here. Second one, 15. Quarter of that have 15 pieces, so quadruple that and it have 16 pieces. Gear 2 have 2 steps, so step 2. $14. I counted all of them. I'm not so lazy, ladies and gentlemen. And we have this big one, third gear. It have It have 15 again, so easier in calculating how reduction relativity is between this shaft and this shaft. This shaft is solid, so this gear. We have 3 set gears. Main shaft 1. It have 20 tooths, and then it's gonna go to 60 tooths, and it have 2 states. Central part of that have 14. Let me read it. 15. So everything can add up. Next one have 16 too. So we go a little bit neither. If it rotates with 1 rotation, it's gonna go for third of this. So 3 rotation of this gonna be 1 rotation of this. its relativity. 1 to 3. Stage 1 of second degree. And same as this. No, not the same. If it rotates 4 times, it rotates 1 time. Relativity with these 2 gears. So, far and far, near and near. If this main shaft of motor rotates 12 times, 3 times 4, 12 times, it's gonna rotate this biggie 1 time. It's relativity of this. Reduction factor is 1 to 12. So, we are done with mechanicals. We're gonna say how many revolution per minute have this, and we assume how many revolution per minute it have. So now we are gonna go some electromechanicals. Some black dots from the marker, and it's not important, boys. If we paint some side of this shaft and we watch it goes slowly, like though something that revolutes with that 3 volt. We can count by number of seconds how many revolution it have visually. And this Hall effect sensor does the same. There is a bipolar magnet under there that have S and N in each half of the coin, and it's attached to the main shaft firmly. And Hall effect sensor are 2 tiny electrical coils which, when these 2 parts passes through them, they change radically in polarity, and electrical current in them changes, and the computer counts the number of changes in these positions, and it will says them how many revolution per minute does it have. How to make and it's all named tachometer. Tachometer says us in shaft how many revolution does in a minute. It's a clock, boys. So how can we make a tachometer? It's easy. How we managed to count this black dot on the shaft visually? So we can attach how we can make a DIY tachometer. Oh shit, I always forget the positive. Positive goes to both sides of this coil. And computer counts this ripples. You remember we draw some black dots to indicate visually how many ripples it's gonna take in some particular voltage. So in the real world you can attach one pole of a magnet like this tape into this shaft, stick to it, forget it. Just imagine the red dot or black dot is south. We have a south in here. So if we pick up an air set and put the microphone fix into near of that magnet, how we can make a DIY tachometer for ourselves. As I mentioned earlier, we draw some black dots in here to estimate how many revolutions per minute it's gonna go in some particular voltage. So imagine we attach some neodymium magnet or some other magnet into this shaft, and this black side is some pole of that magnet like south, and we have a scavenged used headset. We just need a microphone of it, a complete safe and sound microphone. We fix the microphone somewhere around the shaft, and when the south pole or north pole passes through the microphone, we have a spike into diaphragm of this microphone that is a solenoid surrounded by a magnet, and it pushes and catches this diaphragm. And magnet every time passes through this spike is how many repulsions it's gonna take. And how we can calculate that? You plug it into your smartphone and use some sort of audio frequency counter, which there is a lot of them in network, like an app. An app tells what does this microphone hears in every spectrum, even a spectrum that I talk or a spectrum that ants walk. Oh, this buzzing of pushing and pulling the diaphragm of the microphone. And that's our required frequency. And you see, maybe it's 18 hertz. It means this magnet passes through the microphone 18 times in second, and you can calculate that in revolution per minute. I add a video if it's possible to search to knowing more about this shit.